Okay, welcome to lecture. We'll get started here in just a second. Let's give everybody a chance to get in. We are going to be starting lecturing on chapter 13. Again, the lecture notes are up there on Canvas. And again, we'll get started here in just a second. So again, chapter 13 lecture notes are up there online. Just keeps wanting to go. There we go. So if you like for a roll, if you could just type in here like we did last time. So let's have that record in the chat box. That'd be great. Thank you. Okay, just a minute or two here. Let everybody in. Looks like we're getting everybody here, hopefully. Okay, so those just coming in and everything. Again, just like last time, if you haven't done so already, not mute myself there. If you could just type here in the chat box or roll so you don't have to listen to me call everybody's name, that would be good. Also, a reminder as we get going, if you do have any questions during the lecture or anything like that, the chat box is, again, the good place to do that. Your mics, again, are muted, so, we don't hear everybody sort of talk over each other and stuff like that. So if you do have a question, feel free to ask it there in the chat box. And again, even if we've moved on from that slide, just ask it. I'll go back and, try to answer your question, stuff like that. So again, if you're just coming in, if you could just type here into the chat box, if you have not done so already, just for roll purposes, that'd be good. All right. And we should be able to see everything on the screen. Yes. So we're going to go off here to chapter 13 with this equilibrium. Yeah, so it might take a little bit of time for you because you just added in. So it should hopefully show up there. If it doesn't, let me know, okay? All right, so we're going to get started here with chapter 13. And this is our first chapter, and we're going to talk about chemical equilibrium. So again, just letting a few more people in. So I think we got almost everybody here now, I think. So again, if you're just coming in, just in the chat box there, just type here if you haven't done so already for roll. Perfect. All right, so we're going to talk about chemical equilibrium for the fourth time. I think I said that, but we'll continue on here. All right. So let's talk a little bit about the chemical equilibrium sort of condition. And when we talk about chemical equilibrium, what we're really referring to is a certain type of reaction. I'll double check the homework in terms of that. I think I clicked the right box, but I'll double check. But that's probably when the homework will be due. It should be. And usually what that means is a lot of times the due date for the homework, we'll just talk about the homework real quick before we get going. So there was a question on it. So on Al for the homework assignment should be due around the exam day. I think I gave you the next day after the exams to finish the homeworks. But the end of availability in terms of those is the same as the due date. So that's probably why it says it will be inaccessible after 6:29. But it should definitely be accessible now. I'll double check though when I get a chance a little later today. but it should be accessible now, and the due date should be that. But I might have popped it in the wrong box when I was clicking around and doing it, but I'll double check it. Okay, so let's take a look then here at chemical equilibrium. When we talk about chemical equilibrium, we are talking about a specific type of reaction, and that's a reaction such as this, where we have A plus B, for example, goes to C plus D. And what makes this type of reaction is the arrows that head in both directions, and that is usually associated with a reversible reaction. And in a reversible reaction, what we have is basically two directions. We have going from our reactants to our products, which is our forward direction. And in certain cases, those products can recombine and form our reactants, which would then be the reverse direction. So when we talk about really reaching chemical equilibrium, and sometimes people, when they think about chemical equilibrium, they think about it sort of in a way, in the sense of we have pretty much equal amounts on both sides. And that's really not what chemical equilibrium means. Chemical equilibrium basically means that the rate of the forward reaction will at some point reach the rate of the reverse reaction. So what that means is that rate of the forward reaction will equal the rate of the reverse reaction. And essentially what that means is just as quickly as it goes from the reactant side to the product side, it will then go backwards from the product side back to the reactant side. So basically what you get when something does reach equilibrium is the rate of the forward equals the rate of the reverse. And what that essentially means is whatever everybody's concentration is at that particular point in time, or even their pressures at that particular point in time, that means that they pretty much will lock themselves into place. So just as quick as it goes to the right, it will just as quickly go to the back. And essentially what that means is, for example, if we just made up numbers, we'll say here, you know, at that point, A was 4 molar, B was 2 molar, C was 3 molar, and D was, say, 6 molar. And as you can see from this example, it doesn't necessarily mean that when it reaches equilibrium that, you know, we have the exact same amount on both sides. But what it does mean is once it reaches that equilibrium, because the rate of the reaction is equal in both directions, they pretty much will maintain those concentrations. So A will maintain like 4 molar, B will maintain 2 molar, you know, C 3 molar, and so forth, and sort of that made up example. So when we look at something like a beaker, for example, that has reached chemical equilibrium, when we look at it, it may just look like there's not very much going on. You know, it may look like the reaction is over. So for example, if we did an equilibrium reaction where, you know, we mixed a couple of things and it went from, say, a red color, and then when the reaction is sort of done, it goes to sort of a colorless color, which is obviously no color at all. And we may look at that beaker and go, well, I don't see very much happening here on the big level here. It just looks like the reaction is done. But because this is a reversible reaction, you do have a lot of activity that's happening sort of on the molecular level. So on the molecular level, there's a lot of reaction occurring. You have basically this reaction happening going to the product side. You also have the reverse reaction heading back to the reactant side. But the difference is it's going back and forth at the same rate. So when you look at it in sort of the big picture aspect, it doesn't look like there's very much happening. But when you look at it in terms of, you know, sort of the molecular level, there's a lot of activity that's happening. So that's why sometimes we say that, you know, it looks very sort of static on the molecular level, the big sort of picture, but there's a lot of activity that's happening on the microscopic level. And you just have it happening really at the same rate, which ultimately makes it look like there's not much going on. But again, if you could sort of super zoom in to the microscopic level, you would see a lot of activity. You would see a lot of reactants going to products, a lot of products going back to reactants, sort of back and forth at the same rate. So when we look at sort of a reaction that is going to equilibrium here, or going to reach equilibrium, so something like this, H2 plus some N2 makes a little NH3. I guess it's chemistry. I should do a little balancing action there, perhaps. There we go. So in this particular reaction, what we could assume is, initially speaking, we pretty much have all reactants. And that's what we see here in this graph. Sort of at time 0, we have a lot of H2, we have a lot of sort of N2 happening. And in terms of our products, we can see here at time 0, to the left of that arrow, we pretty much have nothing going on. We have nothing happening. So in order to make some of our product here, what has to happen when this reaction begins is we have to have the forward reaction basically taking precedent. So the forward reaction has to begin. And as the forward reaction begins, that's going to require our reactants basically to start to decrease in concentration. We're going to have to use up some of our reactants, obviously, to make our products. And that's what we see here in these graphs. We see the green line starts to go down, blue line starts to go down. But what happens in that process is we are now going to start making our products. So our pink line here is starting to go up, which would indicate that we're making more products at this time. And at some point, we will get enough products that is made that the reverse reaction will start to kick off, right? So at the beginning of this reaction, when it's really that forward reaction that's taking place, at some point here, we're going to get enough products that have been made to really kick off the forward reaction, the reverse reaction to take place. And at some point, what we see here graphically, pretty much everybody is going to plateau out. And that basically means that they've sort of locked themselves into their concentrations at that point. And it's at that point where all these guys, as we can see here on the graph, pretty much level out. That's the point when chemical equilibrium has been made. That's the point where we see that the rate of that forward reaction will equal the rate of the reverse reaction. And again, at the beginning of the reaction, we have more reactants, so the forward reaction sort of predominates. As we start making some products and enough products get made, we have enough products to get that reverse reaction to kick off. And at some point, the rates, again, how fast basically something's happening, that rate of that forward reaction will equal that rate of that reverse reaction. And like I said before, that essentially is where everybody will sort of lock themselves into place in terms of their concentrations or in terms of their pressures. Any questions on that? And again, a reminder, if you do have questions, feel free to ask them there in the chat box. I'm just going to move a couple of things on my screen so I can actually see my screen. Hang on here. There we go. Look at that. There's actually more on the screen I can see. All right. So if we look at this reaction, again, another reversible reaction here. And initially, as we talked about, we have none of the products present, just like we sort of saw on that graph. So we pretty much have none of these guys here. So we are going to get that forward reaction that's going to sort of predominate here at the very beginning. And again, at some point, we're going to build up enough of these products that we can, again, get that reverse reaction to kick off. And again, until we get to that point where we reach the rate of that forward reaction and the rate of the reverse reaction will equal each other. And again, we will reach basically what is known again as chemical equilibrium here. So again, a reminder that it doesn't mean that in this particular example here that we see on the screen that, you know, the amount of H2 and CO equals the same amount of H2 and CO2 at that point. Again, it just means that the rate of how fast it's going back and forth will actually be the things that are equal to each other. And again, here, that's what we see here in this graph. At some point, our forward reaction and our reverse reaction equals. And graphically, that's sort of how you know you reach equilibrium if you sort of graph something like this, time versus sort of rates or time versus concentrations, where everything sort of plateaus out. That's essentially where, you know, we will reach equilibrium. So let's talk a little bit about what is going on here in this particular example. And in this reversible reaction here, if we add more water to this reaction, how does the concentrations of each of these guys compare to their original concentrations? So why don't you take a second there and think about what's going on, and then we'll talk about it. Okay, so let's see what we got going on here. So in this reversible reaction here, if this system is sort of at equilibrium and we add more water to it, which is H2O, what we would expect to happen first off is, let's talk about, so we're going to add more of this guy. Let's talk about what we expect to perhaps happen. When we add more H2O, that should definitely help these two guys come together. And when those guys come together, they no longer sort of has to go hunt each other out. There's lots of water in there, right? You added a bunch of the H2O. And what that's really going to do, it should kick off that forward reaction to happen. So that forward reaction should pretty much kick off in that case. And what that means is, in terms of H2 and CO2, we would expect the concentrations, again, the little bracket means concentration, right? And when we talk about concentration, we're talking about molarity, right? Usually, in most cases, moles per liter. So we would expect the concentration of H2 to increase, and we would also expect the concentration really of CO2 to increase as well. Again, because by adding that H2O, it's going to be kicking off that forward reaction, and we should see a lot of those products being made. Now, in terms of the CO, what we would also expect is we would expect the concentration to go down. So remember, in order to make the products, we need the H2O and the CO basically to come together. So because we kicked off that forward reaction, we would expect the concentration of the CO to decrease while seeing an increase in the concentration of H2 and CO2 in this particular example. Now, one last thing that's there, which is the H2O itself. What we would expect to perhaps see in this situation is we would expect to see probably this pattern. We would actually expect to see the concentration of H2O. It actually would go up at first. And it would go up at first only because you're pretty much artificially adding H2O. So when you add it, you would expect it obviously to jump up in terms of concentration. But once you've added it and the concentration goes up, the forward reaction will begin, and you then should probably see the concentration of H2O also start to come back down, much like the CO over here. But because you artificially sort of added the H2O, you may actually find the H2O concentration being higher than it started with because you artificially added it. But the pattern that you probably should see with that guy, again, is what we see here. It should kind of spike up because you added it. But then as the forward reaction begins, we should start to see a lowering in that concentration, again, because it's going to be needed to make those products. Any questions on that? And again, like I said, usually sometimes you'll probably see in this situation, a nice line there, you'll probably see in this situation that the concentration of H2O may actually end up being a little bit higher than it started. And again, that's really only because you artificially added it. Now, if we look at sort of the same situation over here, but in this case, we're going to add to this reaction H2. And if we add H to this reaction, again, the H2 in this case is on the product side. So we should see sort of a similar situation occurring in this case. Because we added H2, that should again make H2 pretty available there to the CO2. And that should, in this particular case, kick off the reverse reaction to begin. And that reverse reaction would begin. And in that particular case, what we would expect to happen is we would expect an increase in the H2O in this case. We would also expect, again, an increase in the CO in this case, because predominantly what we got going on here is that reverse reaction. In terms of the H2, we would expect it to then go down because we're making our reactants in this case. And for our CO2, I'm sorry, that's the wrong guy there. Sorry, our CO2 should go down. I'm sorry. CO2 there should go down, but our H2 should again follow really the same pattern. Overall, it should probably go down, but we will see it increase because you added the H2. But as it starts reacting in that reverse reaction, we again should start to see it decrease over time. So we can do a lot of things with systems at equilibrium that will affect whether or not products will be made, whether or not reactants will be made, which way the reaction may proceed. We'll see more of this a little bit later on in this chapter. This is really what's sort of known as Le Chatelier's principle, and it sort of governs or what happens when reactions are at equilibrium. Any questions on that stuff there? And again, if you do have questions, feel free to type them in and I'll be happy to answer them. So that's that graph in case you missed the first one. So let's talk about the actual equilibrium constant and its applications. So there is a relationship that we can get from a reaction that is at equilibrium or a reversible reaction. And it's what's known as the equilibrium constant. And the equilibrium constant is this K right here. It is a capital K. And it basically is, as we will see, the relationship of our products divided by our reactants. And that's essentially what we see here. There is a relationship when we do take our products, and again, we do use the coefficient here as the exponent, and divided by basically the concentration of our reactants over here. And again, the brackets do mean molarity. And that equilibrium constant, which is capital K, not to be confused with a small k. Small k is the rate constant, which we'll talk about at the very end of the semester when we talk about kinetics. But K pretty much is what Chem 1B is brought to you by, that letter K. Everything about K is what we're going to learn. KC, KP, KA, KB, KSP. It just keeps going. KF, KW. Any type of K you want to imagine, we're going to talk about it here. So K really is that relationship of products over reactants. And when we do write it, we do use the coefficients in the balanced equation. As you can see here, they do become our exponents when we do it. So it is basically the relationship of the products over the reactants, again, taken to the coefficients as those exponents. And it is an equilibrium constant, which means the value for that K is a constant value. And what that means is when you see a K value, for example, this K value here, that has been given for this particular reaction, that is the value of K that you should always get for this reaction at a specific temperature. So the only thing that really will affect, as we'll talk about, the actual sort of numerical value, if you will, of K is actually temperature. But if you keep the temperature constant, so if you say you did a bunch of different reactions, this reaction here on the screen, if you did it a bunch of different times, different trials, and each time you started with, say, a different amount of N2O4. Say the first time you started with 5 molar, whatever you want to do, 2 molar, 3 molar, whatever it may be. Every single time, as long as you don't change the temperature, the K value that you should get for that reaction should be the same. And that sometimes it's hard for people to sort of understand. They oftentimes will think, well, if I started, say, in experiment 1 with 5 of this guy and 4 of this guy, and then in experiment 2, I started with 2 of this guy and 3 of this guy, I shouldn't get the same equilibrium constant at the end. But you will actually get the same equilibrium constant at the end as long as you do not change the temperature. So as long as the temperature remains constant, the ratio of your products to your reactants will always end up pretty much in the same ratio, regardless of how much of, say, the reactants you started with in that particular reaction. So for example, if you did this reaction at 25 degrees and we'll say the K value is 4.63 times 10 to the minus 3, you could do it again, like I said, 3-4 different ways with 3 or 4 different starting amounts, and it should come out to the same K value. If you do this exact same reaction, but change the temperature to, say, 45 degrees Celsius, you will get a different value of K than you did at 25 degrees Celsius. But if you keep the temperature then at 45 degrees Celsius and did 3-4 different experiments at 45 degrees Celsius, the value of K should remain constant. So again, the only thing that will affect the value of K in terms of value is the temperature. But once you sort of lock an experiment in at a particular temperature, the value of K won't change at that temperature until if you change the temperature once again. So what is K? K is what we calculate here. It gives us some information about what is happening in this particular reaction. So when we do calculate K, one thing, as we will see, one nice thing that we will see is It's just a number. So there are no units associated with K. When we do calculate K, it's just a simple number. And it does tell us something, as we will see, I think, in another slide here, but just to preview, if we get a large value for K, what does that mean? Should we have mainly reactants at equilibrium? Should we have products at equilibrium? If we do have a large value of K, what that should mean is we should have mainly products when we reach equilibrium. If we just think about it mathematically, if you take products divided by reactants, in order to get a large value for K, you need a large number on top, right? Small number on the bottom, and that's going to give you a large value for K, and that means that we should mainly have products. If you have a small value of K, it will mean pretty much the opposite. If K is small, what that means when we take products over reactants, that would mean we would need a large value for the bottom, and mathematically we would need a small value for the top guy. And that means that when we do reach equilibrium, if we have a small value of K, we would expect to mainly have reactants present. So K is really useful because it does give us some idea in terms of a reaction, sort of what's happening, what we should expect in terms of should we have products, should we have reactants. You may be asking, and we'll see it here in just a second, it might even be the next slide, but what is a large value? A large value is basically that big number of 1. So a large value is anything really over 1 is considered a large value for K, while anything kind of less than 1, like we have here in this example, to the -3 would be considered a small value of K. And really, why 1 is chosen, in order to get 1, you would have equal number of products and reactants, right? Mathematically speaking, that would be the only way to get to 1. Here's some other letters in case you don't like A, B, and C, I suppose. So again, as I mentioned, we can use that value of K to help us get a pretty good understanding in terms of a reaction, what we should mainly have there at equilibrium. So again, 1 is considered a large value, anything above 1. So typically speaking, if you have a K value that has a negative exponent, it's typically considered a small value. If you have a K value that has either just a whole number, 100, 200, or even a times 10 to the positive exponent, it's obviously considered a larger value. So take a second here and think about this. If we react here, looks like Mickey Mouse there with a couple of circles. Guess there's a couple more circles and Mickey on his head. If the K value here is 25, what would be favored at equilibrium? So take a second here and think about, should we have reactants? Should we have products? So when you do look at this and you do see K is 25, which is considered a large value. And that should mean, again, as we've been talking about, K is our products over our reactants. So because K is 25, which is a large value, that means we should have a large number on top, and we should expect when we reach equilibrium to mainly have products. Now, it doesn't necessarily mean we won't have any reactants there. We may have a small amount of reactants, may have a little bit larger amount of reactants, but we definitely should be making more products in this particular case. And sometimes you can get a K value that is super large, if you will, or a really, really large number. And what that means is, although it's still a reversible reaction, that means almost 100% of it would be heading to the product side. Just like you can have a K value that is really, really, really a small number, which means for the most part, everybody's hanging out over here on the reactant side. And you can have a situation where, for the most part, even though it's a reversible reaction, it's, almost 100% heading that way. Yeah, so the question is, what does it mean that the product should be favored? So the ratio will not, let's just make sure we clear this up real quick. When we talk about something that's at equilibrium, it does not mean that that ratio of products to reactants will actually be equal to each other. So it doesn't mean that the top guy and the bottom guy will be the same number when it reaches equilibrium. It again just means that the rate of the forward reaction will equal the rate of the reverse reaction. When we talk about the equilibrium constant, what that means is if we have a large value, we should expect more products, which means that mathematically speaking, right, if we take 6 divided by 2, larger products than reactants, we get a 3 for the equilibrium constant, which is a larger value than if the opposite was true, right? If we had 2 over 6, that would give us 1 over 3 there. I'm going to do the math in my head. It's like a 33 and a third. Yeah. So that's like 0.33. And obviously that's a much smaller value for K. So equilibrium doesn't mean that the ratio of products to reactants will actually be equal to each other. Otherwise, if that was the case, there would be no K value because every K value would equal 1, right? So again, it doesn't mean that when we talk about a sample getting to equilibrium, but we could use the actual value to help us determine would we most likely have products there at equilibrium, or would we most likely have reactants there at equilibrium? Right. So yeah, so there's sort of two sort of separate issues when we talk about equilibrium that it's important to sort of keep in mind. Specifically speaking, when we talk about something that has reached chemical equilibrium, we're not really talking about necessarily, how much products and reactants that we have. What we really are truly talking about is more the rate, how fast the reaction is happening in both directions. And when we reach equilibrium, what that means is the rate of that forward reaction, as fast as it's going to the product side, is just as fast coming back to the reactant side. The result of that is, in terms of concentration, is when that happens, that as fast as you go one way, you go just as fast the other way. What that essentially will do is lock everybody into their concentrations. So again, if we look at this one here, if we reach equilibrium, and these were the concentrations of these guys, at that point, once we reach equilibrium, you can see that 7 and 3 is 13 on the right hand side, 5 and 4 is 9 on the left hand side. They don't equal each other in terms of their concentrations, but what will happen when they do reach equilibrium is they essentially will be locked into those numbers until something happens to mess up the equilibrium. So two sort of separate things. When we talk about equilibrium, we're truly talking about how fast the rate of the forward and reverse reaction equal each other, and that should be equal to each other when they do reach equilibrium. And second to that is when we do sort of lock everybody into place in terms of equilibrium, everybody's concentration will pretty much lock in where they're at that particular moment in time. And they really won't change unless something happens to the equilibrium. Other questions on that? So let's talk a little bit about some equilibrium sort of expressions that we could write. So one type of equilibrium is a homogeneous equilibrium. And homogeneous, just like a homogeneous mixture, means that everything is in the same phase. So here we can see everybody's in gas phases. So we could write our equilibrium constant where we take our products over our reactants. So again, the 2 here becomes the exponent here. Coefficient here is 1, which is why there's nothing written here. So we take our products over our reactants, concentration of NO2 over the concentration of N2O4. And again, we would square the top guy there. Now, because these are gases, right, in addition to sort of concentration, a very common process that we deal with gases is pressure, right? Our good friend PV equals nRT, right? All that good stuff. So because this also deals with pressures or gases, we can basically look at pressures and also write an equilibrium expression for that, where this is the partial pressure of NO2 squared, also our products, divided by the partial pressure of N2O4. This gives us two different types of equilibrium expressions. This is what is sometimes referred to as Kc, C being creatively concentration, and this is what is referred to as Kp, which is basically pressure is what the P stands for. So we can write these two equilibrium expressions. They are both equilibrium expressions. They are both essentially the same thing in the sense of they are the ratio of the products to the reactants. But one would deal with concentration. So here would be molarity going into here. And here would be pressure, like atmospheres, right? Going into here. Now, Kc and Kp does not usually numerically equal each other, but they do tell you the same thing. So what does that mean? It means numerically speaking, Kc won't be like 5 and Kp won't be 5, so they won't equal the exact same numerical number. But they still will tell you the same thing like we've been talking about. If you have a large value for Kc or a large value for Kp, they both would indicate that you would mainly have products at equilibrium. If you had a small value for Kc, you probably would have a small value for Kp, and it would also tell you that you would mainly have reactants at equilibrium. And that would also make sense, right? Because if you had a large value of Kp, that means you would have a lot of products being made. And if those products are gases, they probably are going to contribute a lot to the pressure of that situation. And vice versa, if you had a small value of Kp, you would mainly have reactants, and the gas molecules on the reactant side should probably be the major contributors there to the pressure. There is a way to go between Kp and Kc. So in certain situations, you may be given information about just pressures, and they want you to calculate the Kc value, and vice versa. You may be given information about concentrations, and they want you to calculate the Kp. And that's what this formula is here, and you do need to know this formula. So this formula is the Kp is equal to the Kc times RT delta N. So these are some of our normal things here. This is our equilibrium constant for pressure. That's our equilibrium constant for concentration. R is our gas constant, the same one that you use in the ideal gas law. So that's like 0.08206. Or if you used a rounded version there, that's all good too. 821. All right. And T is our temperature in Kelvin. So just like a normal sort of gas situation, right? You got to add 273 plus the temperature in Celsius, right, to get there. And delta N is the change in the moles. So N from the ideal gas law, right, is the number of moles. Delta N is the change in the number of moles of gas products minus the reactants. And that's really important when you do a reaction and you calculate delta N. Sometimes people sort of ignore that aspect of it, that it is the products minus the reactants. And that is, for example, important if you did something like this, where you had 2A plus B goes to 2C. If we were to calculate delta N here, and it's just the gas molecules, it is actually in this case 2 minus 3, which would give you -1. Again, each of these are gases on the reactant side. You could just look at the coefficients and calculate basically how many moles of each of those guys that you have. The negative part of that number is really important because mathematically speaking, if you take this part of the formula here and you take it to the -1, that is very different in terms of the answer that you get if you just go, oh, the difference is 1. The -1 here means you need to take 1 over it, right? The 1 here, you don't have to worry about that. So you do want to make sure that you actually do products minus reactants. You also want to make sure that you do not ignore any of the negatives that you may get or anything like that. It does occur in the gas phase. It also can occur, say, aqueous guys all the way around. So it just really homogeneous equilibrium just means that everybody's in the same phase. This one happens to particularly be in the gas phase. For example, you could have all aqueous guys, and that would also be a homogeneous equilibrium. Yeah, so in terms of the 2 and the 3, in terms of right here, I'm assuming you're talking about. So when we go to delta N in this case, and it has to do with gases, you would want to go to the equation, and you would want to look for everybody that has the little G subscript, right? The G is gas phase. And really, you could just take the coefficient. So the coefficient here is 2 on the product side. That's the only guy we got, which is how we got to the 2 here. On the reactant side, this whole guy here is a gas, and there's 2 of them. And this guy, really badly written G, is also a gas, and there's one more there, and that would be how we got to R3. Yeah. Other questions I could help you with? Okay. So that's a really important sort of formula. It'll allow you, like I said, to calculate one from the other if you're given, depending on the information that you're given. Here. So to sort of answer that other question as well, here we could see this is also considered sort of a homogeneous equilibrium. Pretty much everybody's aqueous. The water really doesn't count because water, in most cases, the concentration of water really won't change. It's constant over reaction. So we really don't worry about water when we're dealing with sort of equilibrium. And as we will see shortly, just to preview and ruin the suspense of it all, really anything that is a liquid or anything that is a solid really will have no effect in terms of the equilibrium constant. So if we did our equilibrium expression like we were doing before, we take our products over our reactants, we would get this expression here. But because water really doesn't change, it really will have no effect sort of on the equilibrium. You can almost get rid of it, and you usually will get rid of it. And the actual correct sort of equilibrium expression for this reaction here, which is acetic acid making acetate and hydronium ion, is our products over our reactants. So everything here is aqueous. And we would leave the water out because it's a pure liquid. So in general speaking, as I mentioned before, we don't use units. And these two guys are not included in the expression. And if you really think about it, because liquids and solids are not going to be included, that really just leaves you two things that are included in the equilibrium expression. And that is things that have the aqueous symbol and things that have the gas symbol. So those are really the two things that you include in the equilibrium expression when you're doing it. And as I mentioned before, in practice, most people don't use units with the equilibrium expression or constant. Again, it's just a number. And really, for the real reason is units really don't cancel out all that great. If you just look up here, if you were to follow the sort of the units that would be here, this would be molarity, and molarity, that would be like molarity squared over molarity, right? And then we would be back to molarity. So sometimes the units really don't cancel out very well in a lot of cases. So typically speaking, if you give it an express K value, it is just the number. So why don't you take a second here and calculate, not really calculate, but write the two expressions for each of these, the Kc and the Kp. So take a moment or two and we will talk about it here in just a second. Okay, so let's take a look and see how we're doing. So on the first one here, we could write a Kc value, and the Kc expression, again, would be our products over our reactants. So on our product side, we have NO2 Again, we do want to take it to the fourth power because of the coefficient that's there. We would also times it by the concentration of O2. Coefficient there is 1, so we don't have to worry about it. Then we would come to our product side, and we do see that the coefficient there is 2, and that would be N2O5 squared. Now, because all these guys here are gases, we can write a Kp value. So the Kp value will look pretty much the same. The only difference is we're not going to deal with concentrations. We are dealing with partial pressures. So this would be the partial pressure of NO2 also to the fourth because of the coefficient times the partial pressure of O2 divided by the partial pressure of N2O5 squared in this particular case, also because of the coefficient. Any questions on that first one there? While I move some things out of the way so we can actually see. There we go. All right, so let's take a look at the second one. We could also write a KC here for this guy, doing the same thing. We're going to take our products over our reactants, and in this case, we will take the concentration of H3O plus times the concentration of F minus divided by the concentration of HF, which is our hydrofluoric acid. And again here, this is water, really a pure liquid, not going to be included here in our equilibrium expression. So this would be the correct Kc value for it. Now, in terms of Kp, you really can't do it because in order to have a Kp, you got to at least have something that's a gas, right? That could generate pressure. So here in B, we have no gas, so we can't do that. So I would say probably in most cases, as you come across, if you can write a Kp, probably almost everybody in the reaction will be a gas. It doesn't necessarily have to be everybody is a gas in there. You could potentially have some type of like decomposition reaction where you have a solid that it perhaps decomposes or something like that into a gas or something like that. So usually you'll need some type of gas involved, obviously, to do a Kp value or expression. Any questions on that? And again, if you do have questions, feel free to type it. Again, even if we're kind of past, I'll go back and make sure. So that hopefully should be what we had going. All right. So why don't you do this calculation here, the equilibrium concentrations for reaction between carbon monoxide and molecular chlorine are as follows. Calculate the Kc and Kp. So why don't you guys work on that? Let me just go back and take a look here at the question, I think. So the question was about the first reaction here. We have, yes, so if you were to calculate the delta N, which you didn't need to for just to write the expression, if you're asking about this first one, on the product side, we do have 5 gas molecules, and on the reactant side, we do have 2. So if you took 5 minus 2, it would be 3 for delta N, if that's what you're asking. All right, so take a couple of minutes here and calculate both the Kc and the Kp value for this guy. Okay, so let's take a look and see how we're doing here. So we want the equilibrium. We have the equilibrium concentrations given to us. We're looking for both the Kc and the Kp value. So obviously, because we're given the equilibrium concentrations, it would make sense to obviously start with the Kc. So we would want to write our Kc expression here. And our Kc, again, would be our products, which is our COCl2, divided by our reactants, which is our CO and our Cl2. And in this case, since we do have all the values given to us, we could just plug it in. So that's going to be 0.14 divided by our CO, which looks like it's 0.012, and our Cl2, which is 0.054. And if we punch all that into our handy dandy calculator, I think I got one here somewhere. Let's see. There we go. Divided by 0.054. Looks like we get something like 216. If you want a significant figure, it is, since it is kind of like a chemistry class, I suppose, like a 220 perhaps on a significant figure sort of rounding. Any questions first off on the first part here? So obviously, you do need to make sure that they are equilibrium concentrations before you would plug it into, um, obviously, the equilibrium expression. Now, once we do have our K C value, like we talked about before, this is where we can use, where are we at there? Our equation here on the bottom that we saw earlier. We could use that the Kp equals the Kc times RT delta N. So let's take a look at that there. So again, our Kp will equal our Kc RT delta N. So to calculate our delta N, again, we want to take our products minus our reactants. So the question is about sig figs, and I was just joking as well, but not really. But um, it is a chemistry class, so you definitely should do the right sig figs and stuff like that. In terms of being marked down a lot or something like that on an exam or quiz, to be truthfully honest with you, I'm probably a little bit more interested at this point in the calculations and so forth. But if it is sort of a problem throughout, say, an exam or a quiz or something like that, you obviously may lose some points. So you definitely should try to do the right sig figs in every calculation that you do. Since in all kiddingness or not seriousness, I guess it is a chemistry class. But truthfully, in reality, if you miss it maybe by one or something like that, you probably will be okay. Probably not going to take off, points. But if it's a problem, like I said, throughout, say, the entire paper or something, whatever you turned in, you might lose some points. Definitely do not give me every single digit known to man, because I've seen that on tests where people write 3.4, 5, 6, 7, 8, 9, 10, and they actually, I even had one guy one time flip the page and write the rest of the decimals on the back of the page. That was how many decimal points they gave. So make sure you do edit yourself like normal, like you probably learned. You should probably avoid a lot of rounding until the very end as well. But you should, obviously, it is a chemistry class, being serious. You should obviously try to get the right number of sig figs. But probably in terms of what I'm maybe more interested in is, how you're doing the calculations and stuff like that. But definitely should try to do those things. So our delta N in this case would be our products minus reactants. So on the product side, we have one gas molecule. And on our reactant side, we actually have two. Again, each of these are a gas molecule. And that would give us -1 for delta N. And that means that our Kp would equal, again, if you use your sig fig answer there, times your 0.08206. Again, you could use 0.0821. I just use that number because that's what they beat in my head and I can't get it out. 74 degrees Celsius, we need to add a 273 to that. So that's a 347 on the Kelvin. And again, all that's going to go to the -1. So we would take 347 times 0.08206, do a little inverse of that, times it by 220, and you get something like a 7.7 on the Kp value. Again, if you use 216 and then use 216 on the other one, I want to say you get 7.6, something like that, if I'm not mistaken. So, you will get a fairly close value as well. But again, you should try to hit those right sig figs. Any questions on those calculations or how we got any of those numbers? This value does tell us a couple of things, right? And we see what we were talking about earlier. The Kc value and the Kp value, they don't numerically equal the same thing, but they do tell us that they are both considered large values of K, which means when we reach equilibrium, we would expect to mainly have products there. Actually, a value of 220 is a fairly large equilibrium constant value. You're going to have pretty much all that COCl2, which then would imply that we would have more COCl2, which means it should be contributing more to the pressure because we would have more of that gas molecule present. Any questions on that? And hopefully what they have underneath is what I wrote. There we go. All right, so why don't you try this one here? The equilibrium constant Kp is 158. What is the equilibrium pressure of O2 if NO and NO, so one of those is NO2. So give me 1 second. Let me figure out which one is which here. Stop sharing here for just a second. And I want to take a looky here and see. Okay, let's see here. The NO2 is the 0.4. So the NO2 is the 0.4 in that particular case. Let me pop back up there. Actually, let me fix it here first. So the NO2 is the 0.4, and let me just fix it here. That should let me do it. Perfect. Pop a 2 there. That should work. All right, so let's go. There we go. That should hopefully work, I think. There we go. All right, so take a moment or two here, and we were looking for, again, the equilibrium pressure of O2. And again, the NO2 there is the 0.4. So we'll talk about it in just a second. Okay, so let's take a look. And so obviously in this case, we're given a bunch of pressures. So we would want to really start with the Kp expression. So our Kp expression, again, is going to be our products, which is the partial pressure squared of NO times the partial pressure of O2 divided by the partial pressure squared of NO2. In this particular case, it is equal 158. So we do have the pressures for NO2 and NO, so we could pop those in, and that would get us 0.27 squared times the pressure of O2 divided by 0.4 squared. Again, because of the coefficient, 158. We're going to multiply the bottom to the other side and divide by 0.27, and that should give us the pressure of O2 will basically equal 158 times 0.4 squared divided by 0.27 squared. And if you do all that good stuff there, you end up with 347, I think, in this particular case. Something like 347. Now, since this is actually a pressure that we're solving for, we do need units, and the units will be, in this case, atmospheres. Any question on that there? We also see a couple of things that we've been talking about. The value of K is 158, which is a large value, which would imply that we should mainly have products at equilibrium. When we do have those products at equilibrium, that means that the products here should be the major contributor to the pressure. And definitely at 347, I think that would be a major contributor to this pressure. Any questions on where any of the numbers came from or anything like that? Hopefully they agree. There we go. All right, so let's talk a little bit about heterogeneous equilibrium. So just like homogeneous equilibrium, good talk. Now let's go back. There you go. So heterogeneous equilibrium means that we basically have things in different phases. So not everybody's in the same phase. So not like before where everybody was a gas or everybody was aqueous. Here in this case, we have some solids, we have some gases here. And in this particular case, as we talked about previously, really the two things that we don't include in the equilibrium expression are solids and liquids, and solids would not be included. So the solid here and the solid here would not be included. So we really would take that out of the equilibrium expression. And that would give us our two sort of correct expressions here. That is our Kc expression, which is the concentration of CO2. And that would be it, right? Because it's just products. There's nothing on the reactant side. Technically speaking, it's the concentration of CO2 divided by 1, which is why we don't write anything there. And our Kp value here, since we do have a gas on that right-hand side there, we could write the Kp is equal to the partial pressure of CO2. So solids and pure liquids, as I talked about, are not included in the equilibrium expression. And that, again, leaves you pretty much only aqueous guys and gases that are included. So why is solids really not included? If you think about it, if you drop a solid into, say, a beaker, it's really not going to react, right? So the only way it could react is if you dissolve it. And if you dissolve it, then it's no longer a solid. It's now going to be something that's going to be aqueous, right? Which then it can react. But it's kind of like if you threw just like a brick into a thing of water, the brick's just going to go to the bottom. It's going to sit there. It's really not going to react with anything, right? And that's sort of the same idea here with the solid. It really won't react. So again, solids, liquids do not include anything that, again, is a aqueous or gas. You do include. Now, if you did have something, for example, say like this. You know, just for example, something of this nature. If we were to write the K expression for this, it would be products over reactants. But again, this is a solid, so we wouldn't include it. So it would then become 1 over A. Yeah? So that would be how you would sort of write the equilibrium constant for that. Again, as you can see what we did here when we have only solids on the reactant side, it's basically just the products. And that's essentially what we see here in this sort of equilibrium. Again, that's solid on the bottom, really not participating, not really acting or reacting with anything, just kind of sitting there. Again, in order for these things to sort of be able to react, the technical would either has to change into a gas or change into a aqueous ion. And at that point, they're no longer the solid, and they would obviously be able to react. And again, that pressure of that CO2, which is equal to the Kp, it does not depend on the amount of calcium carbonate or calcium oxide that's there. Again, the pressure is going to be solely based on the gas molecules that are flying around in that particular container. All right, so let's try one more here. So we've got the partial pressures of each of those gases, and we are looking for the Kc and the Kp value. So take a couple minutes here and see what you come up with. Okay, so let's see how we're doing here. So same idea here. We are given pressures, so we want to probably start with our Kp. So if we write our Kp expression here, again, doing our products over our reactants, that's going to be the partial pressure of NH3, again, since we're dealing with pressures, times the partial pressure of H2S. Here, our reactant side is a solid, so we would not include it. And that basically means that we do have the pressure of each of those. So we're going to take 0.265 and basically square it. And that will get us, we'll call it 7.02 times 10 to the minus 2. Again, here we will not use any type of units as it's an equilibrium expression or constant, so we don't need it. Now that we do have the Kp value, we could use that formula that we saw earlier that will allow us to go from one to the next, which looks something like this. We do need to figure out our N value here, which is our change in moles, so our delta N. On the product side, we have 2 gas molecules, basically 2 moles of it. Coefficient is 1 each. Minus on our reactant side, that is a solid. So that's going to be 0. So our N in this case is going to be 2. R is our gas constant. Our temperature here is already in Kelvin, so we're good to go on that. So we have our Kp equals Kc RT delta N. So the question is, why is it 0, not 1? I'm assuming this 0 here. It's because on the reactant side, it's actually a solid, not a gas. So when we do delta N, it's only gas molecules that are involved. So the delta N is only the gas molecules. So because that guy's a solid, we would not include it. So only those gas guys. So if we did solve for Kc, it would be Kp divided by RT delta N. And if we put our numbers in, that gives us 7.02 times 10 to the minus 2 divided by 0.08206 times our temperature. And we're going to not forget to square it there. And if we do all that good stuff, perhaps. We end up, I believe, with, I'll go this way. I guess not a lot of screen space here. 1.2 times 10 to the minus 4, I believe. In that particular case. Any questions on those numbers, where any of the numbers came from, why we did any of those calculations that we see here? Hopefully they agree, I hope. This also, again, tells us sort of the same thing like we talked about before. Again, as we see here, the value of both the Kp and the Kc value do not numerically equal each other, but they do tell you the same thing. They are both considered small values for K, which both would imply that when we do reach equilibrium, we mainly have reactants that are present. Any questions on that? So let's just talk a couple of ways here to finish out this lecture about ways that we can manipulate K, or sometimes we'll need to use K. And one common way you might remember from everybody's favorite thing, like Hess's law, where you had to add up a bunch of individual equations, right, to come up with an overall equation. So sometimes you do need to add a couple of equilibrium equations together. And you would do sort of a similar thing. Anything that's on opposite sides of the arrow that are the same, that can cancel out or reduce. So if we were to add these two equations that's on the screen here, the C's would cancel out, the D's would also cancel out, and this would give us the overall reaction for these two guys, which would be A plus B equals R goes to E plus F. And if we want to write the equilibrium expression for that guy, it would look just like this, which is obviously the concentration of our products over our reactants, which is E times F times A divided by A times B. Now, how do we get that in terms of our K values here? Essentially what that is taking both of those K values and multiply them by each other. When we multiply them by each other, we can see the C here will cancel, the D here will cancel. That will leave us E and F divided by A and B. So if you have, and it sometimes occurs if you're given several sort of reversible reactions with some equilibrium constants for each of those, and you're asked to figure out the equilibrium constant of a overall reaction that you get by basically adding those guys together. What we do with the K values is we multiply them together. So we would multiply them together, and that would give you the K value for the reaction that you get when you add up each of the individual reactions. So a little bit different than, say, delta H and Hess's law. In Hess's law, you add up all the delta H values, but with the equilibrium constant, what you do is actually multiply the equilibrium constants together. Again, if you're going to sort of make an equation from two individual ones like we have on the screen, could be 3, could be 4, however many you sort of add together, you would then just multiply the K values together. Another very common sort of manipulation that we do with an equilibrium value is sometimes, again, going back to sort of the Hess's law, you would, you oftentimes will just need to reverse a particular reaction. So I think this might answer your question. So if it doesn't, I'll come back to it. But I think this might be what you're asking. So if we have to reverse a particular reaction, for example, like these two reactions here on the screen, the guy up here is one reaction, the guy to the right is really just the reverse of it. And if this was the equilibrium constant for this particular reaction up here, if we reverse the reaction, what essentially is happening is our products become our reactants become our products. So what we do with the K values actually take 1 over the K value. So it's basically the inverse of it, right? Which gives us 216 in this particular example for this reaction here. So if you need to reverse a reaction, again, unlike Hess's law where you just kind of make it negative or make it positive, change the sign, if you reverse a reaction, what you're essentially doing is flipping the reactants and the products around. And as you can see with the two expressions here, they're basically the reverse of each other, right? The inverse of each other. And so how that affects the K value is you would take 1 over the K value. So when we do see a natural value of K, as we talked about, it is specific for the equation we're looking at and exactly the way it's written. So that 4.63 times 10 to the minus 10 would be specific for the equation above it, while the 216 would be specific for the reverse reaction. And maybe just to touch on your point, if we had to do all those things together, for example, if you had to multiply or add reactions together and reverse a reaction, you would then take the inverse of that reaction and then multiply it to the other reaction K value. So you have to sort of keep track of those things. A couple other things just to finish up since we're on this topic here. Sometimes if you remember, like in Hess's law, if you had something like this, the K would equal, again, C times D divided by A and B. If you didn't need 1 of everybody here, but say you needed 2 of everybody, you multiply by a common number. When we deal with enthalpy or delta H, we would just multiply it. But here, what we're actually doing, if you look at the expression, as we go from this equation to this equation, what happens with the K value is it's actually squared. So if you need to multiply by a common number, you would take the K value to that common number. So if you multiply by 2 in this case, we would square the K value. If we multiplied by 3 all the way across, we would take the K value and cube it. And it works the same way if you started out, say, with this equation, and you wanted to get back to this equation. The difference between the bottom equation and the top equation is you divided by 2 all the way across. And the difference in the K value as you would go from the bottom guy to the top guy is the square root, yeah? Okay. So in this case, if we divide by a common number all the way across, you would take the square root. If you divided by 3 all the way across, you would take the cube root of it and so forth. So the way we manipulate k's when we multiply by a common number is we take the k value to that common number. What we do when we divide by a common number is we take basically the root of it to that common number. So square root, cube root, whatever it may be. Any questions on how to manipulate k values? And again, this obviously would be a situation where you're given a number of different individual reactions with k values, and you're sort of trying to build and figure out the k value for an overall reaction. Any questions on that? All right, so we will lay it up here for lecture today. Any questions on any of that stuff that we talked about? Okay, a couple of things before we sort of sign off here for lecture. Ran a little bit long here, so we'll start lab. We'll start lab about 3:10 just to kind of get everybody a chance to get up and stretch and all that good stuff. A couple of things before you take off. We're going to be doing the Excel experiment today. So that should be activity 1. So again, you should hopefully either have your lab manual or you could get it from the chemistry website. And that's what you should be working on. I think we might take a little bit at the beginning just to touch on some of those calculations that was in that review thing. Remember that is also due in like 5 minutes. So make sure you upload that if you haven't done so already on Canvas. And lastly, if you came in a little bit late here to the chat and you didn't type in here for attendance, please do that before you log off. Otherwise, I will see everybody. We'll start it again since we ran a little bit late. We'll start about 3:10, okay? The pre-lab for tomorrow's lab will be up on, it should be up online. It should be on your lab pre-skills is where the pre-labs will be. Yeah, so that's where you want to go. Okay, if there are no other questions, I'll see everybody in about 15 minutes. And the lab invitation, make sure you go through that lab meeting